Okay, so let's start with experiment 08, that is regression analysis. Okay, so we'll start with two examples to understand the concept. Okay, okay. So here, say in x-axis you have voltage, in the y-axis you have current. Okay, you have performed this experiment in your lab in your first year. Okay, V is equals to IR, that is the experiment. What you did, you changed the values of V, okay, different values of voltage, you measured the values of I, different values of current, then you put the data in axis. Okay, so for say for example this is 1 2 3 4 5. Okay, so this is 4 6 2 4 6 8 and 10. Now let's put the value in the graph. So say for example for 2 volt the current was like this, or 4 volt current was like this, or 6 volt current was like this. Okay, for 10 volt current was like this. So this is a graph that you get, and for 8 volt the current was like this. So this is the curve you get, this is the point that you get. So then what you did, you draw a line, you drew a line through these points that intersect these points, right? It should be like this, but due to a little mismatch in the data, some of the points may not exist on the line, but very close, they should be very close to the data. Okay, the interesting thing is here, for example, say for value of 5, you did not calculate the value, you did not calculate during the experiment, you did not, for 5 volt you did not take the measure of current, but from this graph, from this line that you just draw, you are able to understand that this should be the point. Okay, this should be the point of current. Okay, this should be the point of current at 5 volt. Okay, from the curve, from the graph that you just plotted, you can actually extract some unknown data, okay, that was inside the graph. Okay, so this is called interpolation. Interpolation. Now again, say for example you calculated for up to 10, you want to understand, you want to estimate that for 15 volt, say for example for 15 volt, what should be the value of the current. And again, through this line, if you extend the line outside, okay, there is no space, if you extend the line outside, you can also get a point here, and from that point you can estimate the value for 15 volt. I should get this amount of current. What is the value of I? You can estimate from this graph. You extend the line. Okay, this is called extrapolation. Okay, extrapolation. Okay, so this concept is actually, these two concepts is actually stands within a single concept. It is called curve fitting. Curve fitting. So you have some data, you are trying to fit a curve, you try to find a curve that goes through the points you just actually found. Okay, so this concept is known as curve fitting. Now when you have the data is much more clear, much more precise data, okay, so you can do it like this way, because you know that it should go through like this, v is equals to ir, the curve should be a straight line. You are very much clear of the data. It can be other equation, it can be a quadratic equation like this, y is equals to mx square. Okay, it could be like this as well. It is not m, it is x square. Then the curve should be like this, but you still know for value of x what should be the value of y, if you know this one. Okay, so this is actually called curve fitting. You have some points, you are exactly fitting a curve that goes through all the points. Okay, now let's look at a different concept, a different idea. Say for example uh, you want to rent a house, in Uttara, say for example. In x-axis, okay, house pricing, house pricing. So in x-axis, you are putting here number of rooms. Okay, number of rooms, how many rooms are there in that house. Okay, and this is the price of the house. This is the price of the house. say this is my one, this is 2 rooms, this is 3 rooms, this is 4 rooms, this is 5 rooms. Now let's start the value. Let's say 1 room house is, say for example, 10k, 2 room house is around 20k, okay, 3 room house around 25k, okay, 4 room is around 35k. Let's, they are equal distance. I'm just plotting the graph. Say for example, you find a house for one room, it is around, the value is around 15k, okay, 15,000. For 2 bedroom or 2 room, it is around 20,000. A 3 bedroom, suddenly the price is very high, okay. For 4 bedroom, it is a little bit low, not that much. For 5 bedroom, it is also again high. For 6 bedroom, okay, it is a little bit comparatively lower. As you can see in this particular example, this house pricing example, based on the number of rooms, you don't get a linear trend, because the price of the house does not always depend on the number of rooms. There are some other variables, like for example, how many bathrooms are there, how is the view outside, what is the floor, it is third floor or sixth floor, whether there is lift or not. But you are just making an estimate, but based on that estimate you are getting a data like this, okay, the distribution of data like this. So if you try to do this kind of curve fitting here in this scenario, how will it look like? It would look like this, then you connect this, then you connect this, connect this, connect this. So does it actually represent the actual scenario, that the curve should like this, that if you have a room like this, 2 3 4, okay, so anything like, say for example, 2 room or something like this, it should not be here. The value is not exact, that these values are not exact, there are some variability in the data is not exact. So plotting the curve like this way, connecting the data like this way, is not actually accurate. Rather, let's say, moreover, say for example, I have already covered all the bedrooms, right? Okay, let's say you have data with, say for example, 7 bedrooms. So how do you estimate from this curve? Say for example, so it is going like this way, then should I go upper or lower, like this? You are trying to feed the curve like this way, then you are not sure where should be the value going, the 7 bedroom, okay. So what is a better option to feed the data to feed a data like this? Say, instead of doing it like this way, if I draw a line, okay, based on the estimate, let's say draw a line like this. Now let's draw a line like this way. I'm plotting a linear line, but try to understand. So what I'm saying, that based on the distribution that we have, I am trying to put a line that is very close to the, that is close to the points that we have, but not exactly. Then see, I can estimate that, okay, for one value the value should be close to like this, for 2 bedroom it should be close to like this, for 3 bedroom it should be close here. Now there is only, so far we have only plotted 1 2 3 4 5 6, only 6 house. If you increase the data, say for example you try to measure, say for example 100 house, you will see most of the data should be the value, when there is 2 bedroom it should be closer to this line. One of the house may be a little bit higher, but most of the houses price should be closer to this line, somewhere here, maybe somewhere a little bit higher, but it should be closer to this line. So this line is actually representing the trend of the data. Trend means, as the number of room increases, how the value should be closer to, not exact value, but a general trend of the data, what should be a better estimate. And this one is actually providing a better estimate than fitting a curve like this way. This is not going anywhere, okay, rather than this estimate is a better estimate, fitting a curve like this, okay. So this portion, this one, doing it like this way, this kind of trending, this is called regression, okay, this is called regression analysis, okay. So this is actually two different types of curve fitting. So if we actually come back here, so what we are discussing is curve fitting, that is the concept, okay. Curve fitting, okay. It can be two types. One is interpolation, this is one type, and the second type is regression. Okay, so interpolation is 1 and regression is 2. So what is the difference? Interpolation is when the data is much more accurate. Okay, when the data is much more accurate and there is a exact equation, you can find a precise equation for that. Okay, this is actually occurs, this scenario occurs in scientific equation. Say for example, one of the example, v is equals to ir, or say the f is equals to g m1 m2, because these things are fixed, only d was not fixed. So this is a relation, that is f is proportional to 1 divided by d square. So the curve should be like this, because all of these three are fixed value. So the curve should be an exact curve. So when you have an exact curve like this from equation, mathematical equations, then we perform interpolation. But in natural scenario, in different actually practical scenario, when you see there is no linear relation, say for example in case of the house pricing, okay, you can find many other scenario where the exact equation cannot be found, rather there is a variability inherent. Okay, so some of the variability like this, the data can be like this, like this. Okay, there is not a fixed relation. Okay, so in such scenario you cannot just fit a curve like this way. Now this is not a good example, this is not a good exercise to actually make it like this. Rather try to find a general trend in the data, how should be the data should be. Okay, this actually represents a much better scenario, that with respect to x, why should be, what is the most likely value of y, and this is called regression. Okay, and this is actually this experiment, that is regression. The question is, which one is the perfect data, perfect line that you are drawing? It can be this line. You can also draw the line, you can also draw the line like this way. Okay, you can draw multiple thousands of lines through this way. So which one should be the more accurate line? Okay, that is actually here in the regression analysis, and we'll discuss it in the next lecture.